Okay, well, let's take a look at another example for our virtual review. The second chapter that we studied in this unit was on the Pythagorean theorem. We took a look at the theorem as well as its converse, and then we also talked about two special right triangles that the theorem allows us to identify, and that's the 30, 60, 90 and the 45, 45, 90 right triangles. So a typical question that might get asked on an exam would be something like this: which of the following are lengths of sides of a right triangle? Which are sides of a 30, 60, 90 right triangle, and which are sides of a 45, 45, 90 right triangle? Okay, well, let's go ahead and decide what these things are in terms of whether they're sides of a right triangle or not first, and then we'll answer the question as to whether or not they are special right triangles second. So here we go. Let's take this one first. 15, 20, and 25. Well, I can see that if this is going to be a right triangle using the converse of the Pythagorean theorem, then it's going to have to satisfy the a squared plus b squared equals c squared if it is to be right. Now, we would identify then this as our potential for A, our potential for B, and this is our potential hypotenuse. And the reason that I say that is that the hypotenuse, of course, has to be the longest of the three sides. I could assign these as B and A or A and B, however I like, but I just by convention usually order them from least to greatest when I use the converse of the theorem. So we'll go ahead and check to see if it's right first. So 15 squared plus 20 squared, is that equal to question mark 25 squared? So 15 squared, I believe that's 225. 20 squared is 400. And 25 squared is 625. And so we indeed see that it is equal to, so this is a right triangle. Oops, stop that. This is right. Let's try this one next. So let's see, the square 13, the square root of 313, and 12. So right away we don't know which one is longest, so it might be worth taking a look at, well, what is the square root of 313 as a decimal, so we know how to rank these. And I can see that it's about 17.69. So if this was a right triangle, this would be my candidate for C. I'll let this be A and this be my B. So the question would be, is 12 squared plus 13 squared equal to the square root of 313 squared? 12 squared is 144, 13 squared is 169, and the square of the square root of 313, well, the square and square root undo each other, so we're left with 313 as our answer there. Adding these two together, I can see that this is indeed 313. So no longer is this a question mark, it's a check mark. Oops, so this is also a right triangle. Okay, let's check the third one here. Again, it's a little bit hard to see. You might be able to see which one of these is longest, but let's go ahead and pull our calculator up just to be clear. 8 times the square root of 3. It turns out to be about 13.8. So I can see that in this case, the candidate for our longest side, or hypotenuse, would be this one. And since 8 root 3 is longer, I'll just call this one B and this one my A. And I'll go ahead and check it in the Pythagorean, just the a squared plus b squared equals c squared equation to see if it's actually true. So 8 squared plus 8 root 3 squared, is that equal to question mark 16 squared? So 8 squared is 64. Squaring 8 root 3 produces a 64, and squaring the root of 3 produces a 3. And here, 16 squared is going to be, I think that's 256, is that right? Yeah, that's 256. So it looks like we've got 64 times plus 3 times 64, so this means that we've got 4 times 64 here. Is that equal to question mark 256? And I believe it is, but let's just check, and it sure is. So 256 is equal to 256. Check mark. So this guy is a right triangle. And then the last one we have here looks like 300, 300, and 100 root 18. Let's check 100 times the square root of 18. That's 424. So it looks like if this is going to be a right triangle, that this piece here would have to be C, and I would call this A and B. We'll go ahead and check that. So let's see, 300 squared plus 300 squared, is that equal to question mark 100 root 18 squared? So 300 squared is going to be 90,000. 300 squared is going to be 90,000. And 100 squared is going to be, let's see, it's 100 times 100 would be 10,000. And root 18 times itself would just be 18. So it looks like we get, what do we get? We get 90,000 plus 90,000, which is 180,000. And 18 times 10,000, of course, is going to be 180,000 as well. So indeed, this guy is right as well. So these are all right triangles. There wasn't a single candidate that failed. Now the question is, which ones are going to be 45, 45, 90, and which are 30, 60, 90? And hopefully you remember from our course the idea that these 30, 60, 90 and 45, 45, 90 have a special relationship between the sides. So 30, 60, 90 we derived to have this sort of 1, 2 square root of 3 situation where this would be 1, this would be 2, and this would be the square root of 3. And of course you can scale this thing up and down, so you can think of this as being scalable by any factor. And then the 45, 45, 90 triangle have this 1, 1 square root of 2 sort of situation. So if we want to turn these into sort of generalizations, we would think of this as anything in the form, let's see, it would be 1, 2 square root of 3. Here it would be 1, 1 square root of 2, or any scalable version of that where I could multiply these by variables. So oftentimes we think of this as, well, really it's just an a 2a, and a square root of 3 times a. And here we think of this as a, square root of 2a. So a would be any scalable factor. Of course, a could be 1, as it is in the case here. And right away I can see that this guy is a non-candidate because there is no square rooting happening. In fact, this is a Pythagorean triple, so this one is not either a 30, 60, 90 or a 45, 45, 90. The next one to consider would be, well, I mean, right away I see the square root of 3 thing going on here and here, so I would assume this is probably one that might be a candidate for 30, 60, 90. And we'll go ahead and take a look. One way I guess we could check this is to see if it fits this pattern, and indeed it seems like it does. If I choose a to be 8, then what happens is I get 8, 16, and the square root of 3 times 8, and it turns out that's exactly what we have here. So this guy must be a 30, 60, 90. I'm going to go ahead and skip this one for a second and go down to the last one because I see right away it's a candidate for the 45, 45, 90 because, of course, it's an isosceles right triangle. And it looks like what would happen here is I would have to have choose an A of 300. So here I'd have 300, 300, and square root of 2 times 300. And that's the one thing that sort of seems a little bit funky. That I don't have a square root of 2 times 300, but if you look closely, you actually do. If you think of 100 times the square root of 18 as being the same thing as 100 times the square root of 9 times the square root of 2, then the square root of 9 comes out as 300 root 2, which is exactly what we need for that third candidate. And so this one must be the 45, 45, 90. And then I can think about this one, and it turns out that this one can't be either of the two. And the reason that you can look at is that it's not an isosceles right triangle, so it could never be a 45, 45, 90. And its two legs that would be in the I guess the A and the B position in the triangle are not related by a factor of 1 to 2, so this could never be a 30, 60, 90.